In this video, we're going to take a look at some examples evaluating improper integrals of type 1. Recall that type 1 improper integrals are ones with an infinite domain and that they come in three different varieties, all defined in terms of limits as shown here. If we have an improper integral from a constant a to positive infinity of f of x dx, then we can define this integral by first taking the integral of a to b of f of x dx, where b is just some arbitrary constant, and then take the limit as b goes to infinity of that expression. And so this improper integral can be evaluated in two steps. If we have an integral from negative infinity to b of f of x dx, we do something very similar. We first replace the lower limit with an arbitrary constant a and evaluate the definite integral from a to b of f of x dx, and then take the limit as a goes to negative infinity of that expression. The third variety involves both infinite limits, so we have an integral from negative infinity to infinity of f of x dx, and here we're going to define this integral to be the sum of two other improper integrals. The integral from negative infinity to some number c of f of x dx, which is a improper integral like the second one shown here. And we're going to add to that the integral from the same number c to infinity of f of x dx, and this is like the first version here, where we have an infinite limit as the upper limit. And so each of these two integrals are computed using limits, and then we add the two resulting values together. Notice here in this third case that we can pick c to be any real number that we want, and it typically will depend on the integral what value we pick. We want to typically pick a number where the antiderivative of f can easily be evaluated. In this example, we want to evaluate the improper integral from 1 to infinity of 1 over x dx. In order to do this, we notice that our upper limit is infinite, and therefore we know that our first step is to rewrite this as an integral from 1 to a constant b of our function, 1 over x dx, and then take the limit of this definite integral as b goes to infinity. So now to compute this indefinite integral, this is a relatively easy one to compute. We have an antiderivative of 1 over x. It could be natural log of absolute value of x. And we want to evaluate that from 1 to b. And so what we have here is the limit as b goes to infinity of the expression natural log b minus the natural log of 1. And of course, we know that natural log of 1 is going to equal 0. And so we really just have the limit as b goes to infinity of the natural log of b. Now, if we quickly think about the graph of the natural log function, we know that the function goes through the point 1, 0, and we know it is shaped something like this, where it's going to be increasing without bound as we go further and further to the right. And so here we want to take the limit of that function as our variable gets larger and larger, so we want to see what's happening as we're going further and further along the x-axis to the right in the positive direction. And of course, going in that direction, we see that the natural log function increases without bound, and so this is going to equal an infinite value. So what we've seen here is by looking at the definite integral from 1 to b of 1 over x dx, and then taking the limit as b goes to infinity of that expression, we're going to get an infinite value. And so this shows that this particular improper integral diverges. This means that if we were to consider the region under the graph of 1 over x from x equal 1 going all the way to the right on forever, that this region would have an infinite area and we would not be able to compute a finite value for it. In this example, we want to evaluate the improper integral from negative infinity to 0 of e to the 3x dx. First, notice that our infinite limit here is our lower limit. And so that tells us that the first thing we need to do is rewrite this as an integral from a to 0 of e to the 3x dx, and then take the limit of this integral as a goes to negative infinity. So we have a natural two-step process to evaluate this integral. In this case, the first step is to evaluate our integral. And so we know that an antiderivative of e to the 3x will be 1/3 e to the 3x. The 1/3 will counteract the chain rule for differentiation. It will undo that. And so here we want to evaluate that expression from a to 0. We can substitute those values in, and we're going to get 1/3 e to the 0, which will end up being 1, minus 1/3 e to the 3a. We know that 1/3 e to the 0 is a constant equal to 1/3, and so what we need to do is determine the limit as a goes to negative infinity of our second term, 1/3 e to the 3a. If we're not sure how to do this, we can always quickly think of the graph of the function 1/3 e to the 3a. This is an exponential function with base e with a positive exponent, and so it's going to look something like this. And so what we want to know by finding the limit as a goes to negative infinity is what's happening to our function values as a gets very, very negative. In other words, what happens to the function values as we go further and further to the left. And in this case, we can see that that function, that graph, gets closer and closer to 0. And so here, when we evaluate our limit, we're going to get a constant of 1/3, and then our second term will end up going to 0. And so we're going to be subtracting 0 from that, and this is, of course, equal to 1/3. And so here the integral from negative infinity to 0 of e to the 3x dx is equal to 1/3, and this is an example of an integral that converges. Since we have a finite number here of specifically 1/3, that the integral is going to equal. If you'd like to try a similar example, you can pause the video and evaluate the integral from -3 to infinity of e to the negative x dx. Resume the video and see the full solution in a few seconds. Since our improper integral has an infinite value for its upper limit, we're going to rewrite this as the limit as b goes to infinity of the integral from -3 to b of e to the negative x dx. An antiderivative of e to the negative x is negative e to the negative x, and we want to evaluate that from -3 to b. And so we substitute in b to get negative e to the negative b, and we substitute in -3 to get minus a negative e to the minus of -3, and that simplifies to simply adding e cubed when both pairs of double negatives are simplified. Notice that negative e to the negative b can be rewritten as -1 over e to the b by moving the exponential with the negative exponent to the denominator and making the exponent positive. At this point, -1 over e to the b as b goes to infinity is easily seen to get closer and closer to 0, since we have a constant numerator of -1 and a denominator e to the b that's going to get larger and larger and larger as b gets larger. And so the constant over a very large number will get closer and closer to 0 as the number gets larger. And so here we have the limit of 0 plus e cubed, which is simply e cubed. And so our integral, -3 to infinity of e to the negative x dx, converges to the value of e cubed. In this example, we want to evaluate the improper integral from negative infinity to positive infinity of 5 over 1 plus x squared dx. Since this improper integral has an infinite limit for both the upper and lower limits, we want to first rewrite this integral as the sum of two improper integrals, each of which have only one infinite limit. So we want to specifically write this as an integral from negative infinity to some number that we will determine in a moment of 5 over 1 plus x squared dx, plus the integral from that same number to positive infinity of 5 over 1 plus x squared dx. And so the first thing that we need to do is determine what number to use for our upper limit of our first improper integral and our lower limit for our second improper integral. In order to figure this out, it's often helpful to first come up with an antiderivative for our function that we're going to be integrating here. So the function 5 over 1 plus x squared. And this one is actually a relatively simple one. We know that 1 over 1 plus x squared is going to be an antiderivative for the arctangent of x. And so multiplying by a constant of 5 does the same thing here. So this antiderivative is going to be 5 times the arctangent of x. And so this tells us that we want to pick a value that we can compute the arctangent of in order to substitute into, for that, a missing limit in both integrals. And one obvious choice would be x equal to 0, since we know that the arctangent of 0 is going to equal 0. And so because we know the arctangent of 0, we can go ahead and write in 0 for each of these limits. And so now we have the limit, or the integral from negative infinity to 0 of 5 over 1 plus x squared, plus the integral from 0 to infinity of 5 over 1 plus x squared. And we can compute these two integrals separately and then add their values together to get the value for our given integral here. So let's start by computing the integral from 0 to infinity of 5 over 1 plus x squared. Because we have an infinite limit as our upper limit, we're going to take the limit as b goes to infinity of 0 to b of our function 5 over 1 plus x squared. And we know how to find our antiderivative. We already have that. So this is going to be the limit as b goes to infinity of 5 times the arctangent of x, evaluated from 0 to b. And substituting those values in, we're going to get the limit as b goes to infinity of 5 arctangent of b minus 5 arctangent of 0. Now we know this second term, 5 arctangent of 0, is going to equal 0 because the arctangent of 0 is equal to 0. And so what we need to do is figure out the limit of the first term, 5 arctangent of b. We know from limit laws that we can always take a constant multiple outside of our limit. And so what we're left to find is 5 times the limit as b goes to infinity of the arctangent of b. Now, we might know the value of this limit right away just by recalling some basic facts about the arctangent function, but if we don't remember how the arctangent function behaves, we can easily determine it from the graph. We can start by graphing a single branch of the standard tangent function. So a standard branch would go from negative pi over 2 to pi over 2, which are our vertical asymptotes for the tangent function. And our graph, which we know goes through 0, will get closer and closer to both of these asymptotes as we approach them from both the left and right. And so we get a branch for the tangent function that looks like this. So this is y equals tangent of x, not the arctangent. Once we have the graph of the tangent function, we could obtain the graph of the inverse tangent function by simply reflecting this graph across the line y equal x. And so our vertical asymptote at pi over 2 becomes a horizontal asymptote at pi over 2. And our vertical asymptote at negative pi over 2 becomes a horizontal asymptote of negative pi over 2. And again, by reflecting this graph over the line y equal x, we'll obtain a graph that looks something like this. And this graph will tell us everything we need to know about limits involving the arctangent function. So in this example, we want to know the limit as b goes to infinity of arctangent of b. So in other words, we want to know what the function values approach as our variable moves further and further to the right. And as we can see here, this function is going to get closer and closer to the value of y equal pi over 2. And so the limit here, the limit as b goes to infinity of arctangent of b will be pi over 2, and we have to remember we're multiplying it by a constant of 5. And so here we get a limiting value of 5 pi over 2. And so this will be the integral from 0 to infinity of 5 over 1 plus x squared dx. So our first integral has a value of 5 pi over 2. If you'd like, try to pause the video and evaluate the second of our improper integrals, namely the integral from negative infinity to 0 of 5 over 1 plus x squared. You can resume the video in a few seconds to see a full worked out solution. We can rewrite the improper integral from negative infinity to 0 of 5 over 1 plus x squared dx as the limit as a goes to negative infinity of the integral from a to 0 of 5 over 1 plus x squared dx. We know the antiderivative of our function is 5 arctangent x, like it was previously, and we evaluate this from a to 0. We know that 5 times the arctangent of 0 will be 0, and using the limit laws, we see that what we need to compute is negative 5 times the limit as a goes to negative infinity of the arctangent of a. Ultimately, we want to know what happens to the value of arctangent of a as a goes to negative infinity, or in other words, what happens when a is pulled further and further to the left. Well, we can see in the graph of the arctangent that as we go further and further to the left, the function arctangent is going to get closer and closer to negative pi over 2. And so our limit as a goes to negative infinity of the arctangent of a will be negative pi over 2. We multiply this by the constant negative 5 to get a value of positive 5 pi over 2. Now that we know this value, along with our integral from 0 to positive infinity, we can go back to our original improper integral and add the values together to evaluate our desired integral. So as we've previously seen, our integral from negative infinity to infinity of our function is equal to the integral from negative infinity to 0 of our function plus the integral from 0 to infinity of our function. And we've computed both of these integrals on the right-hand side. We've just seen that the integral from negative infinity to 0 will be 5 pi over 2, as well as the integral from 0 to pi will also be 5 pi over 2. And so the final value of our integral is 5 pi over 2 plus 5 pi over 2, which is equal to exactly 5 pi. And so this is an example of an improper integral that converges, in particular, converges to the value of 5 pi.